Great stuff. Hi, everybody, and welcome to the May QGIS Open Day. I'm really glad everyone's been able to join us for this amazing session. And after missing last month's session, it's really good to have everyone tune back in. Please feel free to ask any of your questions in, of course, the live chat. And I have put the meeting link into the live chat if you would like to, of course, join in the Jitsi meeting. Please do so muted so that there's no background talk as we go through the session. So the session for this hour is really fascinating. So it's on imaging spectroscopy and using that data in QGIS, as well as the challenges and opportunities associated with using the imaging spectroscopy data in QGIS. So I'm really excited for this presentation, and I'm going to hand over to Benjamin to take us through it. Over to you.
Yeah, thank you, Amy, for this introduction. I start my presentation now. You can see it now?
Yeah, perfect. I can see great.
Nice. Okay. Yeah, and as mentioned, the topic of my presentation is imaging spectroscopy data in QGIS. A complicated word, and yeah, it's a presentation not only prepared by me, but also by my colleagues, Andreas, Fabian, and Sebastian, and Patrick. We are from Humboldt University in Berlin and the University of Greifswald, also in Germany, and both. What is our background? We developed a QGIS plugin called the Ammobox, and which you see here. It is to be used with remote sensing data, and without going too much into the details, this presentation focuses more on the backgrounds, why we need this plugin, and what are we using it for. And yeah, Amy mentioned it in the beginning, imaging spectroscopy. What is it? What does it mean? Complicated word. And yeah, it is related to spectrometry. Spectrometry means the way of measuring radiation that is reflected, that comes from an illumination source and is reflected from a surface or materials, and then gets measured by a sensor like this one that has a cable. This way brings it to this field or to this measurement device here, and then collects how much radiation is returned from this or reflected from the surface in different wavelengths of the electromagnetic spectrum. And these tools can also be used in the field, like here. This is my colleague Marcel, who is doing measurements in the grassland area. So we can do field measurements, but not only for agriculture, but also in other, or basically in any kind of environment. What do we get from these measurements? We get profiles, so-called spectral profiles, like we see them here, which show us how much radiation was reflected over certain wavelengths. From usually we measure the range from 450 nanometers or 4.5 micrometers to 2.5 micrometers. This here in the beginning is the visible light that we can see with our own eyes, but here we have the near infrared, and this is the short wave infrared. And as we see here, these spectral profiles differ between different materials. For example, a typical vegetation profile like this green one looks much different than compared to bare soil that shows us a spectral profile that is typical for minerals, or here, of course, snow. And if we make measurements over water, then we get much less reflectance. And in particularly in the near infrared, there's almost no light that is reflected anymore. And what we see here in this plot as well is that it's not only that the general profile differs, but also within these parts, within specific wavelengths, we might have specific differences. For example, depending on the amount of water that is inside the vegetation, we may see differences here in this part of around 1 micrometer, for example. And for geological applications, it might be of interest to look into these wavelengths, because they tell us something about how is the surface that was measured, which type of minerals do we have inside. So we can do, if you have specular profiles of such a good resolution, so we have many measurements along this over this wavelength range, then we can do very precise descriptions of these profiles. And for example, go into such a valley and measure it and describe it by doing some calculations. So in general, we can say the higher the spectral resolution, the more measurements we have. So we have here usually, if you want to have a spectral profile like this, it consists usually of around 2,500 data points. This is a typical number of these that is generated by these field measurement devices that we have seen in the previous slide. So the more measurements we have, the higher we have the spectral resolution, the better it is, the more detailed we can describe differences in surfaces. And these surfaces can be measured, but we can also simulate them, like in this tool. This is a tool that is available in the Ammobox QGIS plugin, where you can simulate such spectral profiles by changing, in that case for vegetation profiles, by changing vegetation parameters like chlorophyll or the water content or the leaf area index, which means how many leaves are stacked over each other by the plant. And you can see, okay, how different this spectral profile will change across different wavelength regions. And in turn, we can assume that if we exactly know how such a profile looks like, we could measure it and invert it, this model, and to derive these parameters that you see as input for a model. Let's go back to the field. So Marcel is doing a single measurement, but he is doing a lot of them in a row, and then he goes forward to measure more and more and more. Quite time-consuming work, but in the end he gets a kind of an array of measurements, and this is a structure that we are quite used to, that looks like a raster image, and in fact it is like something that sensors can generate, and because these spectroscopy sensors that are able to make many measurements in a short time are called imaging spectroscopy sensors. So they are usually mounted in planes or on satellites, and what we get out of them are data structures, image structures like this one. So data cubes, where we have the 2 dimensions x and y, so the spatial dimensions, and the third one is the z or the band dimensions that you can see here and visualize. So we have many bands, not only many pixels, but also many bands, and this can be visualized like here in this other image cube tool of the Ammobox to get a better idea of this imaging spectroscopy aspect. I mentioned that there are sensors that do make these spectroscopy measurements, imaging spectroscopy measurements. So they can be mounted on planes. So this has been done since a couple of years, but now more and more we also have space missions that do collect imaging spectroscopy data. For example, the MMAP sensor that was this space sensor. So it looks like here on this image, and there's another one, the Prisma sensor. It's an Italian mission. What you see here in this diagram is again the wavelength regions from 450 to 2,500 nanometers. So here we have the visible and the near infrared. Here we have the short wave infrared. The gray areas in the background are those ranges where we have a higher transmittance of the atmosphere, so we have the chance to collect spectral information at the sensor because it was able to pass the atmosphere. And here we have different sensors which you might already know, like Landsat is a very popular, or the Sentinel-2 sensors, and their wavelengths and which wavelengths regions they receive information and collect measurements. And for these sensors here, so-called multispectral sensors, they do not have many bands, or they have a couple of bands, 10 to 15 maybe, and usually a single band covers a quite broad range of wavelengths, like here from Landsat 8. And compared to that, these imaging spectroscopy missions have many for bands, and each band usually covers only a very narrow range of radiation. Like here, for the MWEB sensor, which has more than 200 bands. And compared to that, this is our field spectrometer carried by Marcel, and here with more than 2,000 bands. These are currently active missions, and future missions are in the planning, like CHIME or the soil biology and geology missions of the NASA, which will become operational in the future years. So we can expect that there will be more and more data, imaging spectroscopy data generated or made available in future. So why do we want to use QGIS for working with such remote sensing data? First of all, my personal way to start QGIS for remote sensing was on a field trip in the Brazilian Amazon, where I realized that QGIS is a very nice tool to visualize raster data and vector data together, and to navigate also in field, to do field work, like here. So that was my start using QGIS for my work. And in general, we all know it's free and open source. It's nice. We can not only we do not have to pay much money for, but also it's we can look into the source code and to understand what it is doing, which is very important often. And it's easy to use and to integrate into other workflows that use software from the open source community. QGIS itself has provides a powerful ecosystem of plugins, or there are other very good and sophisticated plugins specifically for task and remote sensing, and in particular we have a powerful application programming interface which we can use to create own graphical user interfaces to applications, but also we can use the QGIS processing framework, we can use the API, the Python API, and we can start our processing algorithms from the command line interface. You have seen this tool before, this ImageCube tool. It is realized with if you are a programmer, QGIS programmer, you will have recognized many parts that are provided by the QGIS API. For example, here to get the colors for these surfaces, we use the multi-band color renderer and the single-band pseudo color renderer, which you know from standard QGIS, and these specific widgets to select the layer source and the extent and so on. Yes, but back to the data side of imaging spectroscopy. Where do we get this data from? This is a screenshot that I showed at the QGIS user conference in 's-Hertogenbosch in the Netherlands a couple of weeks before, where I tried to get imaging spectroscopy data for, and using this data portal. But I failed. Of course, there exists data, but I did not have the access rights to get it. So I downloaded an MMAP image from another part. So this is Sertogenbosch, the place of the user conference. I was able to download for the demonstration an MMAP image here from a region more thorough. And in this slide, you see a couple of challenges we are confronted with, which are not related to QGIS, but generally to imaging spectroscopy. So the first one is, okay, there's not much data available so far. There will be more in future, but so far it's we have to wait for future missions, and also for more observations by the existing data missions. And then if we have the data, then usually the coverage is not very large compared to this Landsat image in the background, which has a width bandwidth, not bandwidth, but a swath, so-called swath of 180 kilometers. Here we have a swath of 30 kilometers only. Both images have the same pixel resolution of 30 meter, but here the coverage is obviously much smaller. And then, because we have so many bands, that means we also need quite a certain amount of data storage to store all this data. So it's only a part of the MMAP image covers only a small part of the region of the Landsat image, but is almost half of the data size. I will here you see this. Why does it look that red? Here I used a different band combination. I show the near infrared, the shortwave infrared, and the red as RGB combination. So it's very common in hyperspectral remote sensing to use this band combination to highlight the vegetation features. And I used this representation for all the MMAP data on the next slides, and the true color visualization here for the Landsat data. And which other challenges are there? For example, what we like to do is to compare the pixel profiles, so which we have seen on the previous slide. So, and if you use standard QGIS like here, we have the Landsat image in the background and the MMAP image in the foreground, and these are the profiles returned by the QGIS Identify Results tool. The blue one, very tiny here, very short, is relates to the Landsat image in the background, and that one, the violet ones, to the MMAP image. And obviously, it's hard to compare both because they are plotted against the band number only, but not the wavelengths, which we would like to see to better compare these profiles. And another problem is that with imaging spectroscopy data, we have many bands, and this makes somehow also the selection of the right band complicated. Usually we do not exactly know which band number relates to which wavelength regions we are interested in. And this is somehow something you usually do not want to recall, which band of these more than 200 bands is associated with which wavelengths. And that's why we created the Ammobox, which you see here now in the background. So a QGIS plugin that allows us to visualize different images side by side. For example, to compare them, like here. So this is the MMAP image that you have seen before. It's an airfield in the Netherlands, and I click on different points, and we can compare here in this plot the spectral profiles between the Landsat image and the MMAP image. So in that case, we compare the band number. We compare these profiles by band number, and now I change it to the wavelengths, and which makes it much more easier to compare these profiles, because here we see the differences in the near infrared and the shortwave infrared between the Landsat image, which has less data points because it has only, I think, 8 bands, and the MMAP image with its much finer spectral resolution. And we can Yeah, and if we know these the wavelengths that is associated to each band, it makes many things. So we can do something like these plots here, but also we can use this wavelengths information to automatically select suitable band combinations for better visualization. Where is this wavelengths information, which is very important for us? Where is it stored? There's no convention on or standardized way to describe it. So it's there in the GDA library, for example, there's no specific function that returns us such wavelengths. So there are different data formats and different data providers, and everyone makes it somehow different to provide which wavelengths the raster band relates to. This is one example that's commonly used, very old way of describing imaging spectroscopy data. It's a so-called NV header format. It's a text file, basically. It's not XML, it's not JSON, it's a simple text file that describes the wavelengths here and also other band-specific values of interest. A more recent approach is the spatial temporal asset catalog way of describing such image metadata, which I like pretty much because it's not only for electro-optical properties, but properties of geospatial data in general. So, and it's more consistent. It's based on JSON files, and definitely something we want to have look more into the detail. And but how can we use these metadata in QGIS? Yeah, so far it's a bit problematic because we can only see it in the layer properties and the information board here. So, but there's no good way to exit this from the QGIS API. There, for example, you see here, this is an issue in the QGIS issue tracker. It's open for almost 10 years now as a feature request. So what we would be happy with to get something like this. So this QGIS API, so you have the raster layer object, and you can get the band count for, and also the band name for a specific band of interest. And we would be happy if there could be a way like to get the band wavelengths, for example, and the wavelengths unit for a specific band. Maybe we can implement it somehow in a good way that is accepted by the QGIS developer community. If you are interested more into, that was my wrap up of or short introduction into imaging spectroscopy. If you are more interested into the details and backgrounds and also applications, where do we use imaging spectroscopy, agriculture, hydrology, geology, for example, then I can recommend you this EO College portal. It has it collects a couple of good tutorials and lectures related to remote sensing in general, also to radar remote sensing, and within this HyperEdu e-learning initiative. There are now, or thanks to this initiative, there are now also many lectures about the backgrounds of hyperspecular remote sensing and theory, but also application. So and of course, there's the Ammobox. There also here you find the documentation on Read the Docs related to the Ammobox that we develop. And so if you're thanks for your attention. If you have any questions, don't hesitate to write us an email. This is one is mine. And if you have any questions, then I hope I can answer them.
Brilliant stuff. Thank you. Alrighty, it's nice to see everyone commenting in the live chat. Hi, John. Hi, Raymond. Nice to hear from you. And hi, Aaron. There is an interest. They are mentioning that the reflectance profile model tool is really cool. So that's pretty awesome. And then So I'm going to start off the questions because I think this is such an interesting tool to use. And I have a bit of background in invasive plants and that sort of thing. And I wanted to know how specific you can get with that signature. Because in South Africa, we have a problem with an invasive species called water hyacinth, and it creates these sort of large mats of the plant over water areas. Now, it could be really useful to use this sort of signature of that plant to kind of track where it is using the spectroscopy. I got it right, yay. So how specific can we get using those signatures? Or is it just a case of this is a plant and this is a rock?
But I don't know specifically for your use case how far you can go, but in general, that's the idea that imaging spectroscopy allows us to make more differences within the same type of class, so within the same type of application, not application, but type of surface. For example, I know from agriculture, so it's very, there are many studies that show that it's very useful to differentiate between the same type of vegetation, but different conditions, vegetation conditions. And yeah, you have to see it for each single use case. And but probably, yeah, I would give it a try in your case. So
that sounds amazing.
I do not know specifically, so but if you yeah, but could be a good chance. Yeah, I probably the problem is more to get the data for that allows you to map it by now. But in maybe 5 years or so, the situation will look much different compared to today. And of course, you might have the chance to get in aerial observations where the imaging spectroscopy sensor like HIMAP or so is mounted on the plane, or even on a drone and so on, which makes the data availability much better for you. So, and yeah, but in general, yeah, that's your use case looks like a typical application for using imaging spectroscopy data. Of course, yeah.
Brilliant stuff. All right, we have a question coming in from the live chat from Raymond. What did you use to generate the graphs in your presentation? What program?
PyQGIS. Because yeah, it's why didn't we use MATLAB? Because MATLAB is not so we wanted to have we looked, okay, what is available, and at that time it was PyQGIS, which was most integrated into the Qt framework, which we used anyway for the graphical user interfaces, and specifically to have more not only to show a plot, but also to provide some interactions with, okay, mouse and user interaction with the plot. We think that still PyQGIS is one of the best and most and fastest frameworks to use. But there could be also QCharts, but it's not compiled with or not deployed with QGIS, unfortunately, which would be even better, maybe more integrated into the Qt framework. But yeah, PyQGIS.
Okay, cool. Alrighty, so Grant Boxer, also in the live chat, I'm also pasting them into the actual chat so you can read them as well. So he says, I am keen to look at using the Prisma Nmap data for mineral mapping. I believe that the NGeoMap app has been written, but we would need spectral end members.
End members, yeah. Okay,
put into a map. Any thoughts?
What is an end member? Yeah, it's this is now a very often used technical term in imaging spectroscopy. An end member is kind of and it's a pixel that is very distinct for a specific type of land cover that we want to see, so that it's really clear this is forest or this is that type of vegetation. This is an member for apple trees, for example. And then there might be a different other spectral profiles which are show more a gradient, because it's not really clear. Is this entire 30 by 30 meter pixels covered by forest vegetation, or maybe we have shrubs inside and open meadows, grasslands, and so on. It's not an end member, but end members are really clear pixels, and they are often used for to unmix other to estimate, for example, fractions of other land covers or biophysical variables. And we need to do spectral end members to put into the app. Yeah, deriving end members is an application domain specific question. Yeah, so it's so far, yeah, I'm not that. He mentions the application NGeomap. NGeomap is an application that is developed by the GFZ in Potsdam, so not by us, but it's and it is then a part of the Ammobox application. So I'm just responsible to get it running there, but I don't know really how it works and so on. So we don't program it, but yeah. Grandboxer, if you have more, yeah, feel free to write us an email. I know your name from the issue tracker, so it's one of our users that provides a good feedback. Thanks for that. Yeah.
Awesome. Great to hear from you, Grant. So then next we have another question from Aaron. Thank you for the presentation. Great looking plugin. The Cube Visuals window is something I've wanted to use. Does it let you plot? Oh, wow. Spatiotemporal data. Wow, my dyslexic brain. Really, Aaron? Spatiotemporal data. So that data takes a long time.
No, so far it doesn't, and it was for this plot I used also Pythongraph, which offers some 3D functionalities. It's very complicated if you are not a professional 3D programmer. So it's still more kind of a proof of concept than an application that you can use with any type of data. But of course, yeah, spatial temporal surfaces, for example, is something that we want to we plan to integrate or to allow users to visualize in the future in the Ammobox as well. Spatial temporal data, yeah, could be an additional slider that allows you to shift this cube in time to compare observations from made over the year or so. Yeah, it's an interesting idea, of course. If you just want to compare images that, for example, time series of real-world sensing data, there are other plugins related to this in QGIS. Earth observation time series viewer, for example, and there's also a second one that uses Google Earth Engine data for. Yeah, just ask for in the QGIS plugin installer, you will find them. And yeah, but so far the Ammobox tries to focus on the imaging spectroscopy aspect, and so time series is not that, so far was not our focus there.
I mean, for example, with areas that change over time, so for example, a deciduous forest, that image spectrum would obviously change over that time because you're going from like really broad green leaves to very little of anything. Yeah. So it could be quite interesting to see that change over time. That's the only sort of aspect I could think of for that use case.
Yeah, yes, of course. I mean, that this common. It's a common use case, and we use this in my lab. So it's very common to derive phenological profiles, which show us how, for example, a vegetation index changes over the years. So for that, we do not use imaging spectroscopy data, but we use multispectral data like Landsat and Sentinel-2 time series, and for which we have these high number of observations that allows us to describe these temporal profiles over the year. And there's also here, for example, if you This is this specular profile plot tool in the Ammobox, and some on the previous slide I showed you how I changed the unit that is plotted on the x-axis from band number to wavelengths. But there's also the option to change it to a date timestamp or decimal year. So in principle, this tool can also be used to show temporal profiles. Yeah, it's of course, yeah, it's in other studies also we use it. Maybe it's not the focus of the Ammobox plugin, but of other our QGIS plugins, and also in our analysis we use this temporal information, these temporal profiles quite often to describe to differentiate surfaces and land covers and describe vegetation conditions, for example.
Awesome. Grant mentions that he'll shoot you an email, and it's no problem, Aaron. This is half my job, is reading off the screen. I don't see any other questions in the live chat currently. So does anyone in the room with us, Neil, Victoria, Emma, do you have any questions for Benjamin?
No, I'm fine. Thank you. Great presentation.
Thank you.
No question on my end, but I just wanted to say that it's a great presentation, and I'll be very keen to follow up on like what the use cases come up going forward using the plugin. Yeah.
Brilliant. Thanks, Neil. All right. Oh, well, that then brings us to the end of this session. It just leaves me to thank Benjamin for coming through and showing off this really fascinating talk. I can't wait, like Victoria says, to try it out. And thank you for coming in and spending the time with the QGIS Open Day this morning. The next session will start at 11:30, so go and grab a cup of tea and don't miss the next session. Thanks everyone for joining.
Okay.
Cheers.
Goodbye.